Okay, so in this video, we're going to look at conducting one sample hypothesis test in R. And to start with, we're going to go through and do it manually. And then we're going to look at some functions that can take all of the work out of it for us. So to start with, we're going to look at our z-test. Now, the z-test generally should only be done when you have known population standard deviations and a large sample size. So this is a situation where you don't do this on a regular basis. Generally, with one sample test of means, you would do a t-test. But this is usually where textbooks start, and so we want to walk through that example. The test statistic that we calculate for the z-test is x bar minus the mean of our hypothesis test divided by the standard deviation for the sampling distribution, so the standard error. And so we're going to go ahead and we're going to use the MT-CARS data set to walk through this calculation. We want to test whether or not the mean is greater than 20 miles per hour in our MT-CARS data set. So the null hypothesis is the mean is equal to 20, and the alternative hypothesis is that the mean is greater than 20. So we're going to calculate x bar, which is going to be the mean of our sample from the MT-CARS data set. And our sigma, we're going to assume for this calculation that the population standard deviation is about 6. Again, we're assuming the population standard deviation simply because that's what you do with the z-test. You have to have that population standard deviation given to you, or you shouldn't be running the z-test anyway. And then our mu0 is the mean for the null hypothesis. So we're going to set that equal to 20. And then n is going to be the length of our data, MT-CARS MPG. Oops. Forgot my assignment operator. There we go. I was wondering why true. And then finally, our z-test is going to be x bar minus mu0 divided by sigma divided by the square root of n. And the z-score we can get from our list of variables here. It's about 0.085. It's not very big. And so we can use the p-norm to calculate the p-value. So we want the z-score as our probability, as our value that we want the probability less than. We want the lower tail, and we want that to be set to be false because we want the actual upper tail, because we want to be greater than 20. Oops, I want to run that. And we get a p-value of 40.465. That is obviously much larger than any significance level that we would set. And so therefore we would fail to reject the null. We would conclude that this is not strong evidence that the mean MPG is bigger than 20. Now, normally you don't want to actually do these hypothesis tests like manually calculating out every step. You would prefer to use a package. And so there is a package that has a z-test in it, and that is the package that goes with the Basic Statistics and Data Analysis textbook, BSDA package. Again, you'll need to go to Tools to install this before you can run it. But I've already installed it, and so I'm loading the package. And they have a function z.test, mtcars, mpg is the source of my data. The alternative is greater, and my mu is 20, and my sigma, that's the mu naught, by the way, and the sigma dot x is 6. And again, you have to specify it. You can't calculate it from the data set, or you shouldn't be using the z-test. And if we run this, we get our z-test here, and we get the same p-value rounded to 3 decimal places that we got here. Our mean here is provided, the mean of our sample. And this confidence interval appears to be a one-sided 95% confidence interval. Now, if we're doing a test of proportions, we would also use the z-score, or the standard normal test. Not the z-test, but I mean, it is a z-test because it does use the standard normal distribution, but it would not use this function. Instead, we would use the prop test. So for this one, we're going to look at the VS data set column or we could use the AM column in this data set, because those are 0, 1 variables, which basically means they're yes, no's, they're success and failure type of variables. So I'm going to use the VS column. And so I'm going to store X to be the sum of mtcars VS. That's essentially going to tell me the number of successes in that data set. So the number of ones. And then the length is going to be the sample size. And then my prop test, I'm going to specify the number of successes, the number of total samples, the probability that I want to test my hypothesis against. In this case, I'm going to see if this is different than 50%. So the alternative is equal to two-sided. And if I want to use the correction factor, I can say correct equals true. And if I run that and I get this output, again, this has the continuity correction. That's what that's about. I can turn this off if I don't want it. But the p-value that I get is 0.59. So that's kind of high. And the confidence interval I get is also specified. This is assumed to be a 95% confidence interval. The sample estimate here is 0.43 from the sample. Now this p-value is very high, even though this seems like it's a lot different than 50%, just because the sample size is still pretty low for proportion problems. So the sample distribution is quite wide, and you can see that the upper bound here does include 50%. That's just how wide the confidence interval is. So these hypothesis testing functions, you can also use them not only to test hypotheses, but you can also use them to construct your confidence intervals for these corresponding scenarios. Now, you can also use another version of calculating this, particularly when you have small sample sizes, the binom test. Which has similar syntax. And again, you get similar outcomes. The number of successes is 14. The number of trials is 32. The p-value is basically the same. And the confidence interval is also basically the same. So again, you can use the binom test for particularly for small samples, or the prop test for typically you would use that for larger samples. Now, to do the t-test for means, again, we're going to do this test on the mtcars data set. And I'm just going to specify X is my mtcars MPG for this example. And then I'm going to run my t.test function. X mu is the null hypothesis mean. So I'm going to do the same test that I did for the z-test. And I'm going to test the alternative equals greater. And again, you can do less as the other alternative. But since I know from previous videos that my mean is in fact slightly bigger than 20, greater makes more sense. And again, when you run this, you're going to get an output for your one sample t-test. Here's that same, the probability value is very close to what it was with the z-test, because the sample size is over 30. Again, your confidence interval doesn't appear to have an upper bound, which I find interesting. But because this p-value is greater than 0.05, then, or whatever alpha value you would prefer for your significance level, it does fail to reject the null hypothesis. Now, another thing that we can test here when we're doing these hypothesis testing is that particularly for the z-test and the t-test, we do make the assumption that the data is normally distributed, and so we may want to look at the normal probability plot and see how closely it is normally distributed or not. And so we looked at in previous video how to make a QQ plot from ggplot. You can also make a QQ plot from the base graph functions. And so this would be QQ norm X, since this what I stored mtcars in there. PCH equals 1, so that's just the plotting point style. Frame equals false. And then that's just the dots for the data. And then I can add the line, QQ line, X, comma, and then I'm going to color them steel blue. And the line weight V2. And so again, we add the line here so that you have that straight line to compare it to. In QQ plot, in the ggplot, you would use the geom line in order to add the line to the dots. But here we've done QQ line adds on to the QQ norm graph, that blue line that you can see here. And I've seen worse in terms of normal distributions. This doesn't look very normal, but like I said, this is not, if this was really, really very skewed, these points would be way, way off the line. And so this isn't great, but it's not obviously terrible, let's put it that way, in terms of satisfying the requirements for our hypothesis test, that it is in fact normally distributed. If you wanted to investigate the normality further, there are hypothesis tests specifically for testing normality of plots, but that we're just beginning hypothesis testing, and so those aren't yet available to us. We may circle back around to them later on after we are more comfortable with doing hypothesis tests. You could absolutely do things like goodness of fit tests or other kinds of tests, rather than just visual inspections of the normality. You could also make a histogram or something like that in order to get, again, some sense of the way that the graph is distributed. The data is distributed.